in place. And so this says linear regression finds a regression vector B that maps a predictor X to a predicand Y using the equation Y hat is equal to XB, where the hat indicates an estimate. You'll see that in the literature quite often. To contrast PCA and regression, please describe the regression objective. Click all that apply. Regression is used for exploratory analysis of X. Absolutely. Regression is used to find important signal in X useful for describing Y. Yes, in fact, that is its mathematical objective. Regression is used to explore the linearity of signal between X and Y. Yes, you can see that if you've got residuals plots that show a distinct trending or show a nonlinearity potential. And regression is used for identifying a model that can be used for process monitoring and control. Yes, it can. That's one of the big things that people use it for. Okay, coming back to here, I wanted to show the RMSE-CV and the RMSE-C. And I'll put the last couple of comments on here is that one of the things that we would look at here is this drop is we would ask ourselves, is that statistically significant? Looking over here, knowing that we're measuring in inches and RMSE-CV is in the units of the Y block, so it's in inches. Could you measure to, 0.001 inch with that pneumatic level detector? Maybe not. So it may be that you would back up to using 3 latent variables instead of 4, because you'd say that just doesn't look like it's capturing something significant, and it might just lead to a more brittle model because I'm trying to describe smaller variance in X as well. Okay. We can also look at our statistics for the model, looking at calibration fit by right-clicking in the white space and saying show on figure to get this particular plot. Okay, we talked about this table in terms of number 4. That particular amount of variance might not be statistically relevant. But one of the other things about this particular table is you'll notice that in PCA, these were organized by large to small, whereas that's no longer the case here. Instead, it's really the product of this one and this one are being organized from top to bottom. So that's a little different in the PLS models. Regression vectors. Remember we looked at the MLR regression vector, this yellow one, and we saw this ringing in the coefficients. And we said that that was due to the ill conditioning in the X transpose X. Well, that's ill conditioning doesn't look like it's affecting our regression vectors here for PCR and PLS near as much. In fact, it looks like we have important regression coefficients right about where the action truly is in the temperatures in the thermocouples due to changing levels, whereas at the bottom and in the plenum, we're seeing less of a significant regression vector coefficients. You also notice that the PLS and PCR regression vectors are fairly similar, and that's not unusual. The performance of the two techniques is often comparable, even though PLS tries a little bit harder to get relevant information in the earlier factors, earlier latent variables. The algorithm for PLS is shown here. This is one of the NIPLs, nonlinear iterative principle ALS. I can't even remember what NIPLs stands for. Oh, it's down here. Partial least squares. So we calculate a weight from X times U. Well, if we just have one Y, then U is just Y. And we normalize it to be of unit length. And we get a score vector. And Then we do U times T, which is, this is our Y, to get our loadings vector in the Y block, et cetera, et cetera. And I think you guys should probably memorize this. The real point of this slide is to show that the algorithm really isn't that difficult. But the most important part to really remember is that PLS is finding relevant information in X while trying to predict Y. And there are other algorithms. There's lots of them. There's a really nice comparison by Martin Anderson of 9 different PLS algorithms that, if you really want to get in the math. If you look at a real fun one called Simples, the weight vector turns out to be just the eigenvector of this cross product between X and Y transpose X. And it uses what's called an orthogonalization of a Krylov sequence. It's faster than Nipol's, and it's actually quite accurate as well. So the important thing to remember is that PLS finds a basis R with factors in X correlated with Y while describing large amounts of variance in X. To kind of give a different sense of how these different techniques are working, MLR, PCR, and PLS, you can look at it graphically like this. On the left-hand side, we have Y being plotted essentially as a surface plot above the 2 variables in the X block, X1 and X2, that are being shown over here. And you can see these are lining about an ellipse, and that as you move off in this direction across the ellipse, that Y increases. And so you would think this would make for a good regression problem, or regression is possible here. If you do MLR, well, this is the PCA plot of the X block data. If you do MLR, the regression vector is shown here. So if you project all of these X variables, all these samples, onto this regression vector, you get a distance. And that distance is correlated with this plane here. So I can plot essentially my prediction, Y prediction, as a plane across X1 and X2. So this is going to be my MLR regression vector. You'll notice that we're color coded. The dark ones are below the plane and the light ones are above it. PCR, of course, the first principal component lies right along the first principal component. The regression vector falls right on the first PC if we do a 1 PC model. And if we do PLS, it has its first, if you use just a 1 latent variable model, it lies in between the two. So between MLR and PCR. And that's what we were saying, is that the basis in X is being described in PCR by PCA, MLR by the correlation with Y, and PLS does something sort of in between. And one of the things that Simon DeYoung came up with, the guy who came up with the Simples algorithm, is that PLS is the regression vector that is perpendicular to the MLR vector. If you drew a line that's perpendicular there and bring it down and touch this Hotelling T-squared's surface, PLS is the vector that has the longest projection onto the Hotelling T-squared on that particular line that's perpendicular to the MLR regression vector. Another technique that we use.
Hey, Neil,
Yeah.
I had a question that'd be interesting to. So there is the NIPALs or the SimPLS algorithms. The question is one better suited for any specific scenario? I do spectroscopy. Any preference for spectroscopic data?
In terms of regression, what I like about Simples is it's fast and accurate. The reason people will like NIPALs is that it's really easy to deal with missing data because you can impute in the algorithm quite easily. So I think that would be the biggest difference.
Thanks.
Okay. Multivariate Y. We can do PLS for multivariate Y. Interestingly, if you think about MLR, for example, you could do multivariate Y block as well for MLR. The thing is that it's identical to using, as many variables as you have in the Y block, different models, univariate ones. That's exactly the same thing for PCR. You could do multivariate Y, and it'd be the same as doing a whole bunch of PCR1 models, if you will. And the reason being is that the basis in PCR is being determined using just X. It doesn't consider Y. In PLS2, we can model X and Y essentially as scores and loadings, much like your bilinear model in PCA looks. And now the basis that we're obtaining here, that R basis, does depend on Y. So PLS2 is not the same as a whole bunch of different PLS1 models. But PLS2 can provide a nice regression fit. Here's our scores in Y and our scores in X, and you get your regression vector here. It's now a regression matrix because you have multiple Y values. The place I think where this really works well is when you have a lot of Ys that are correlated. So there really isn't a whole bunch of individual or independent Y variables. And so now I'm doing sort of looks like a PCA model to capture that correlation structure to a smaller number of variables. So that's probably where that makes the most sense to use PLS2. And what it sort of looks like is that if I've got an X block, I could get my first principal component as this red line.
No sé qué pasó. No se conectó de nuevo porque
Thanks, Scott.
llegó el internet.
So the first weight vector that we're using in the X block is actually a rotation from the first principal component. It's going to be more relevant for describing what's going on in the Y block. Whereas the Y block, you can see this is our first principal component as well. And this would be its first loadings vector in the Y block. You get your scores, and you just do a least squares fit between the two scores. And it's really that simple. We talked about our root mean square error measures, and now a little more detail on these things. So RMSE, root mean square error, we have calibration, cross-validation, and prediction. And RMSE is really given for all of them, can be written like this. The RMSE CV, we can break out into the subsets, and I'll show you that shortly. The nice thing about RMSE is that it's in the units of the Y variable, and you have a sense for what the error is in the Y variable, so you can use that to your advantage. I mean, you have a better sense of what's going on. Other people use the correlation coefficient, and this is, you'll probably see that more often in the statistical literature or from somebody who really likes statistics a lot, is that they'll be more interested in what R is. The problem for us as engineers is that it's unitless. It considers the range of Y, so there's some times where even a real poor model can look like it has a good R squared. Whereas up here, we're in the units that we really like. And Bob Roginski is on the call, and so he really harps on this one and can jump on me for if I don't say it quite right. But the idea here is that imagine that you've got a process that you're working with, and you've got a process control engineer, and he says, well, what should I control this to? How tight should I set my controller? And you'll say, I want an R squared of 0.98. Well, that doesn't mean much to that process engineer, but if you told him I want to control it to plus or minus 0.02 inches, he'll be able to say, yeah, we can probably do that, or no, we can't do that. So the units are very useful, and it's the RMSEC numbers are very closely related to the estimation error as well. So the root mean square error of calibration is really a measure of fit, RMSEC. And so what we really want to do is have a measure for the fit, but it's not sufficient. We're also going to want to look at the predictive ability on new data. And that's what the other two statistics are. The RMSE is measuring an average deviation of the model from the measured data. And RMSEC is a measure of the fit. So remember, as I kept the number of latent variables in my PLS model or my PCR model, the fit improved like crazy, while the RMSECV might have started to increase, suggesting that I'm overfitting. You could come up with any nonlinear model you want to, and you can refit the data perfectly. In PCA, you can refit your calibration data perfectly just by keeping all of the principal components. But not all the PCs are really relevant for describing the underlying fundamental physics of the measurement system. And that's a huge point here. So don't kid yourself by looking at just the fit. We're also going to want to look at things like the RMSECV. Here I split it out into its subsets. We're now the J's, so we're going to sum over the J's, the subsets that we're going to split into. This is an estimate of the predictive power on new data. That means that I'm getting an estimate of how well I can work in the future based on the fundamental physics of the system, not based on just doing a mathematical fit. So RMSECV, of course, is doing a round robin on the calibration data set. So it's not really perfect in terms of evaluating or validating the predictive performance of this data. And that's why we get a brand new data set, something that's statistically independent of our previous measurements to validate our data, our model. And now we're really looking at the predictive power. So RMSEP is the prediction error based on data that the model was not used to calibrate the model. And you have to be careful about that, because in the old days, when people were doing artificial neural nets, one of the things that they would do is they would hold a validation set out and they would calibrate their data, their model, until the calibration set or this validation set that was left out of the fitting process was minimized. So the validation set was actually used as a part of the calibration procedure. And that was reported as the error in the modeling effort. Whereas in that case, the validation set is not statistically independent of our modeling effort. And so you would need a third one to look at. Okay. We talked about RMSE as a function of PCs or latent variables. And the optimum number of factors might not necessarily correspond to the global minimum. So keep in mind that some of these things still might not be statistically significant, and you may want to back up so that your model is not brittle in the future. In our example with the RMSE or our slurry-fed ceramic melter, we can look at the RMSEC, CV, and P for each of the three modeling approaches. And you'll notice that the calibration error was lowest for MLR. Well, that was the objective. That was what MLR tried to do, was fit the data as best it could. In cross-validation, it looks like PLS is the lowest. And in RMSEP, principal components regression might be considered the lowest. And there's going to be subtle differences in the structure of the data. There are times where the test set might actually have lower error than the cross-validation from our calibration. Well, imagine if you had a test set where all the data points were close to the mean, and you're not really exercising the model very well because all the data is at the mean. You could have a potential where the prediction error is lower than the cross-validation error.
Neil, we had a couple of questions in the chat.
Oh, yeah.
First was, is RMSE a measure of linearity? And so we kind of discussed that one in chat, saying that no, it's not. I wonder if you wanted to comment on that.
Yeah, I agree. It's really not a measure of the linearity of the data. Instead, I think you'd want to look at the trends in your Y residuals. That would be a better indication of linearity.
Great. And then the second question was, if I have Y values in the range 1 to 3, and my RMSE CV or P is 0.1, how reliable are the predictions at both ends of the Y range?
I'm assuming that you've mean-centered your data, and so you're getting an RMSE CV of about 0.1, and that the estimation error is actually directly related to the RMSE CV at the mean of your data block. The leverage has to be considered as you move away, and it generally larger. Some of my experience is that with these models, it hasn't been hugely larger, but it tends to be bigger. And we have a tool in our I really want to get back to here. We do have a tool where you can get rid of that, make a plot. You can show the error bars. You can make an estimate of the estimation error, if you will. And I'll get rid of the calibration data. That makes pretty messy. The calculation is a little involved, and those are guesses. What I would always caution about is that the error estimate that you get, like the RMSE CV, is sort of like an error in the prediction, right? Whereas these estimation errors also have an error to them, and it's tends to be, let's see, to the fourth power, whereas the RMSE CV is to the second power. I think that's a reasonably accurate description. So these estimates are exactly that. They're just estimates. Don't use them as gospel.
Thanks. And that was with the little checkbox, show error bars on the plot controls when panel.
Yeah. Thank you.
Thanks, Neil. Interesting.
You bet. I think it really, really is important to understand that fit and prediction are two really different aspects of a model. Fit is important. It's necessary, but it's not sufficient. And you've really got to validate your models. And if you attempt to publish anything, on a regression set of results, and you don't include at least RMSE CV and hopefully RMSE P as well, it's very likely that the reviewer will fail the paper.
One last question.
Yep.
Well, not last question, but most recent question.
Another one.
Is there a measure of linearity in the relationship? Can you, let's see, where did that question go again? Oh yeah, is there a more appropriate measure of linearity for a PLS model?
Yeah, probably. I don't use them much, so I can't really comment. Maybe somebody else could.
I think one thing that's always useful is if you plot the actual Y against the predicted Y, if it's curved, then it's a good indicator that there is a nonlinear relationship. Because if it was a linear relationship, that those points should fall along a straight line approximately.
Yeah, and you should be able to see that residuals versus measured as well.
Yes, and residual plots
Yeah.
show that too. Thanks.
Okay. I wanted to show something else that corresponds to, remember I said, what's the error in the reference? And I'll try to get an estimate of that. So let's go to the limit of RMSE, and we can just write RMSE as this equation where it's, the sum of squares, average sum of squares of the measured and the predicted. And I can put my predicted in to this equation. And then we can say, well, let's say that Y is going to be a true, something that we'll never know, but it's true, plus an error. And we'll also assume that the model is perfect, such that our model's at predicting the true, and we'll substitute this into the equation. So you get Y true here, plus the error is this portion corresponding to this model there. And our model's predicting the truth, i.e. our model's perfect. Well, you can see that the RMSE, the number that you get, is going to be the error in your reference value. So even though your model can theoretically be better than the actual reference error, you can't prove it with this RMSE type of an approach. You may have to try something else. So that's as good as you can get. So as you think about doing pre-processing, changing pre-processing, changing your measurements, et cetera, well, at some point, you've reached your limit given the approach that we've got here to prove that you're doing better. So if the model's perfect, the RMSE goes to the error in the reference. The number of factors to keep, principal components, just remember that the choice is not always simple, but future prediction is really our goal, not fit. Our rules of thumb is that we're going to do cross-validation and split the data into about the square root of the number of samples. It's useful to try different cross-validations with different data ordering, and hopefully you would get a reasonably similar answer across those. If not, you may have outliers, and that's going to be the subject of Thursday's course. If we have time series, we're going to use block cross-validation. Be conservative. Models are more often overfit than underfit. The best choice is often not the global minimum press. We often will look at the minimum of the press and work backwards if the improvement is not at least 2%. Well, yeah, that's just a rule of thumb. If the calibration error is less than the cross-validation error by a lot, and here we're saying 20%, it suggests that we're overfitting. So there's watching the cross-validation errors start going up while the cross-calibration is going down, we're probably overfitting. We're also going to look at the variance captured in X and Y and ask if it is significant with respect to what is known about the errors in the data. So know something about your measurement errors in both the reference and the measurements that you're making. Up here we've got time series. We use block cross-validation. If you have designed data, we'll often use custom cross-validation techniques as well. And that would be the end of that section.
I had a question come in. If I get a prediction from PLS model beyond the upper and lower limit of my Y range, should I dismiss these numbers, or is there a way to make sense of it? And Bob answered basically saying that you are extrapolating in that case, and so treat that with some caution.
Yeah, and that's right. You can extrapolate in two ways. You can look at your Hotelling t-squared. You're also going to look at your Q residuals. If the Qs are high, you're definitely not going to trust it. if you're not too far out of the range, often you can probably say you're okay, but you start getting a long ways away, then it turns into a problem. I know that people say Beer's law, works. It's linear, and so therefore extrapolating a little bit isn't too dangerous. But the Q residuals is going to be really important on that one. So in other words, we're a little more flexible in the extrapolation, but there's no hard cutoff.
Thanks.
Yeah. Okay. I do have another set of polling questions here. So I'm going to try to get my poll up, but meanwhile, here is the question. I'd like folks to think about this. See if I'm clear. It's not cleared. Okay. So I'll read it to you, and then I'll let you think about it for a second, and then we'll talk about it. It says identification of B, the regression vector, is often referred to as calibration based on a learning set. Multiple linear regression is the most obvious and simple way to identify B using this equation here. B is equal to X transpose X inverse, X transpose Y. Why wouldn't we use MLO all the time? And this is a real question. I've been asked this by people who are very good in spectroscopy. Wow, we did really well.
Neil,
on
did
time.
you
We're a
share
little
the
ahead of
polling question?
I can't clear the polling. It's locked up.
Right, so we're basically just doing the polling verbally
Right.
Okay.
without input from
Somehow after
participants.
first
So what
question
we can
went
do
up,
is
the poll
we can pass the ball to one of us, and Neil, you can send us the question on Slack, and one of us we can actually conduct the poll if you want to.
Yeah, sure, we can do that. Oops, I gotta stop sharing to do that. You want to try to clear that, Scott?
Sure.
I just the special characters don't show up if you pull. Let's see.
Okay, let me make you presenter again.
Okay. I will try to upload it then. I'm going to view my poll. Okay. How's that? Do you see it?
Nice.
Yeah. I think that got interfered with when I was sharing. I'll give folks 5 minutes and we're getting there. think we're supposed to have the. Oh, what's the show? Alex Trebek music going. Bob, did I discuss the R squared appropriately?
What, you were waiting for me to jump in and rant?
A little bit.
Well, in retrospect, when I did that, it was my timing was off because I would do that during the CLS example where you right click and you showed the figures of merit. So I hadn't even discussed the root mean squared error metrics at the time, but yeah, I think got the point across that in general we're not big fans of R squared. It's not, at least for the problems that we work on, it's not all that useful.
I guess necessary but not sufficient. Even if you don't answer it on the poll, try to go through the question. Okay, looks like we're slowing down here. Oh, I'll quit at the end of the minute. How's that? Nope, it looks like most of you are done. Let's see how we did. Oh, I probably locked it up. I tried to show poll results. Okay, can you guys see that?
Yeah, we can see the results.
Okay, I'm gonna back over to here. So PCA showed that the predictor block is not full rank. And that's true. You know, if X was not full rank, we probably wouldn't use MLR unless we do something like a stepwise regression to try to identify a set of variables that might work. So even with computers, it's difficult to calculate X transpose Y. I'm glad only one person said that. That's actually the easiest part of that equation. And unless you've got really super big data, but if we do, then we're going to have a hard time with that inverse as well. Everybody really liked the X transpose X is rank deficient condition. That's correct. That one is why we don't want to use MLR. And the inverse of X transpose X doesn't exist. Well, we wouldn't use MLR then either. So that's good. Let me save those results, and then we'll load up our next one. Okay, I'm going to put this. Am I sharing my screen?
No.
Okay. Cross-validation question. Let me share my screen so maybe you can read it over here easier. Oop, did the poll disappear?
Looks like the poll is gone.
Okay, so when I shared, the polling disappeared.
Well,
It disappeared before that.
Okay.
Now it's back.
That's fun. I'm glad you guys are trying to answer these things. think cross-validation is an area where the discussion could go on for a very long time. Oh, I can see the Eigen guys are trying to answer these too. Okay, you guys are starting to wind down. We're getting there. Okay, I think I got all the people that want to answer. I'll close the poll, show results, and we'll talk about it. Okay, so cross-validation, why do we use it? Check all that apply. Starting on the bottom, cross-validation helps avoid model overfit. That's true. That's one of the reasons why we use it. Cross-validation provides a measure of fit. Well, it really is attempting to try to give you an estimate of prediction. But you have to be careful because cross-validation is applied to our calibration set. And so we do have to go out and use a separate statistically independent test set to truly validate our model. Does it provide insight into our regression model's expected estimation errors, model performance? And the answer is yes. In fact, that came up as part of one of our questions that came back to this figure here, where the RMSE-CV is actually about what the estimation error is expected to be at the model origin, the mean of the model. For example, if you mean centered, it would be at the mean. So yeah, cross-validation can help find metaparameters such as number of latent variables to use in PLS. And yes, that's true as well in PCR and a number of other techniques. In fact, it's used in nonlinear modeling as well to try to help out find what the best metaparameters are. And the last one is cross-validation can be time-consuming, is therefore a potential waste of time. If you have a very large data set and you're trying to use a very complicated nonlinear model with lots of metaparameters and you're trying to span over a wide variety of parameters, and some of them probably just don't make sense for the problem of interest, then yes, it can be a potential waste of time. But if you have done your PCA, you've done your exploratory analysis, you have a really good idea of what kind of parameters might be useful for the problem, then I'd say it's not a waste of time. It's exactly what you need to do, and it needs to be included as part of your modeling effort. Okay, with that, I want to see if the Eigen guys have comments or if there's additional questions.
No new questions, but I will comment on that last one about the cross-validation and being in cases where it might be a potential waste of time. Maybe not exactly that same word as a waste of time, but I agree with what you said, that for some, especially of the nonlinear modeling methods, it can end up, especially if you have a large number of splits in the data set or a lot of submodels being built, it can end up taking so long that it's not really practical to do. And in that sense, you may end up killing the calculation after you get tired waiting for it to complete. So I just agree with what you said. But yeah, definitely for these linear methods, it's so fast that it would rarely be a waste of time for those faster methods.
Yeah. Okay, excellent. If there's more questions, that's fine. If not, one of the things that we are going to do is talk about outliers and other model diagnostics and forensics on Thursday. I think, Scott, you said that the recording will be done today or tomorrow probably, and an invitation for Thursday will be sent out either today or tomorrow as well.
Yep, that's right. It sort of depends on WebEx, so either later or late this evening or tomorrow morning.
We have a question come in, Neil.
Yeah.
Can you speak more to the option about avoiding model overfit? I thought that some cross-validation methods can lead to model overfit if you don't choose the right one for your data set.
That's true. In fact, probably the most common one is going to be leave one out cross-validation. And just for the fun of it, let's take a look at this cross-validation curve here. I'll get rid of this. And there's our RMSEP as well. I'll spawn this out. This is, a live shot, so I don't know if this is going to work out or not, but I'll leave one out here for PLS. Let's see, let's spawn this just so we have a picture of it. Close that. And I'll change my cross-validation, leave one out. I've not ever done that with this data set. So this will be fun. But this is actually one of the ways that our leave one out tends to be fairly optimistic. And so if I get rid of RMSEC, leave one out is saying keep 5. And down here, if I get rid of this one, it's saying keep, no more than 4. Oops, I'm trying to zoom in. So you can see how leave one out was more optimistic there in saying keep 5 instead of 4. And even down here, we were trying to back up from it to maybe even 3. So does that make sense? Bigger data sets, we don't do leave one out. Hey, some days the magic works.
Okay, thanks. Another question. Can you describe what is meant by factors calculated sequentially by projecting y through x? That PLS on slide 54.
Yep. Let me go back. That slide. So if you look at this particular comment, projecting y through x, now let me go to the algorithm on 59. So you can see that what I'm doing here is I'm calculating a weight vector. So I start by saying, let's put y in here. Let's say I just have a univariate y. I put that in there. I get a weight vector. I calculate scores. The loading is just going to be a 1, or it's not used in PLS 1. But I get a score in y. And now what I can do is calculate loading. I get a score, and I deflate, if you will, my x block down here. So I take x, I subtract the score and the loading. And the loading is really just the projection onto the score. So anyway, I deflate. Okay, so now I've removed rank from my x block, and now I take E and I come back and I put E in here and I do it again to get another Y. Go through the whole process, we deflate again. Boom, deflate again. So we're constantly removing the signal that we've identified earlier and trying to pick out smaller and smaller chunks of the X block sequentially. Did that make enough sense? Or did maybe I was too undetailed?
Hopefully so. Can you go back to slide 54 to see that statement?
Yeah. So vectors are calculated sequentially by projecting y through x. So x is deflated, we project y through it again, deflated. If I get to
Thanks.
here, there's some detail for you. There's some algorithms. So you can see this as well. There's the Nipal's algorithm. Oh, dang it. Just for this question, you can see where I'm deflating the X block. And then we put the next version of X up through. So that's actually the algorithm. Take a screenshot of that if you want. Okay. Any other questions? Donald, you're muted.
Sorry. Dang. No. Well, let's see. There was one more question. Are these scores relating to the last one? Are these scores and loadings of the weight vector? Sorry, are these the scores and loadings of the weight vector?
Actually, yeah, the scores come from the weight vector. You can see here in this algorithm, the score is actually calculated off the weight vector.
Well, there's a follow-up that I need to think some more about this before I can ask useful questions. And yeah, I can certainly sympathize with that.
Yeah, me too. And then the loadings are really just a least squares projection onto the scores. And in fact, that's also true in PCA. It's just that here our scores are going to be different than the PCA scores. So of course, then our loadings are going to be different.
One last thing, Neil, that might be kind of fun to show, sort of relevant to comparing different model types, is the use of the model optimizer, taking a snapshot of the model once you've built it.
Oh, you know what? Can I pass you the ball?
Let me see, do I have MATLAB open here? Sure.
Okay. Where, gotta find you.
Every donal.
Yeah. I just passed it to Scott. There you are. My list is so long I couldn't see you.
Okay.
Did I give it to you?
It says I'm presenter.
Okay.
Let me know if you can see my screen. Or do I need to?
Not yet. You got to share, I think. There you go.
Okay. Yeah. Sorry, I wasn't wasn't expecting to present, so this may be a little rough. But so if I've built a PLS model, I'll just do it really quickly here. This is also my secondary computer, so it's a little slow. Great. And I'll pull up the same demo data set that you were using, the second of the slurry-fed ones.
Sorry, I put you on the spot. I think you're a lot more familiar with that tool than I.
So I just double-clicked on the slurry-fed data set in the demo data sets, and that automatically loads the 4 data sets, the calibration X and Y, and the validation X and Y. I'll build a model. And it doesn't really matter what we're getting here, numbers of factors and such. I just wanted to get a model. So the icon up here for taking a snapshot is very useful for saving a model for comparison with other models. So if I click on that, just click on the camera icon, it starts the model optimizer, which is a new window. And you will see the entry for that model. So let's not dwell on that for a moment. I'll just quickly create a second model. And to do that, I'll just go to the menu in the PLS analysis window and change it to MLR. And then it keeps whatever pre-processing and cross-validation I had, but is now going to be an MLR analysis once it, okay, so I think, yeah, just wait for the title at the top of the bar to show that it's switched to MLR, and click on the model icon. And it will build an MLR model. And then I will click on the camera icon to take a snapshot again. And this time it just adds it to the existing model optimizer window. So you can do that for many models, and especially if you're using the same calibration data sets and validation data sets, then you get a nice summary of the relevant quantities like the RMSE CV, RMSE C. You may have to make these a little wider to see the full title. So you get a nice summary of those, and not very useful when you have just 2 models, but if you had 20 models here, that can be very useful for, I can right-click on that and sort in one direction or another and see which model or combination of pre-processings and such will give the best results. That's all I had to say about that.
I think that's
Very
awesome.
useful tool.
Yeah.
So I will, oops.
And you know, we do a comparison between things like PCR and PLS, and invariably somebody will ask, so which is better? And a really nice study was done by Peter Wenzel and his group, where they looked at a whole bunch of practical data sets and tried to identify which was better. And they discovered that really nobody's a winner. So in the end, understanding how they work underneath is useful, and then you get good at one of them, and then the rest of them you can just try them. But just getting good at one of them is really the best first step. So I'm, I have heard people say PLS is better, but maybe not.
So I've stopped sharing. If you wanted to share for any summary screens or anything, all yours.
No, I think I've pretty much got it. So if there's no more questions, I think we can draw it to a close.
Great. And we'll reconvene on Thursday.
Yeah.
Thanks, Neil.
Thanks, everybody.